All right, welcome to the deep dive. Today, we're cracking open the Online Encyclopedia of Integer Sequences, the OEIS,
Hmm.
and we're looking at a sequence that, well, it sounds pretty niche, A000347,
It does. The title is Number of Partitions into Non-Integral Powers.
non-integral powers. Okay,
Yeah.
so straight away, that's different from standard partitions, right, where you're just adding whole numbers.
Exactly. Usually you think, okay, how can I sum integers to get, say, 5? 1 plus 4, 2 plus 3, that sort of thing.
But this involves fractional powers, like square roots.
Precisely. Things like square roots, cube roots. It's a much more generalized idea, and it fundamentally changes the game.
And you see that change reflected in the numbers. The sequence starts at offset 4, so A4 is just 1. Seems simple enough.
Right.
But then it goes 5, 24, 84, and looking way ahead, a 40 is what, over 107 million?
Yeah, the growth is staggering. It tells you immediately that whatever we're counting, the possibilities just explode very, very quickly.
So this abstract idea, partitioning into non-integral powers, how do you even count that? It sounds incredibly complex.
It does sound daunting, yeah. And that's where the OEIS is so valuable. It often provides context that bridges these abstract ideas to something more concrete.
Okay, so there's a bridge here, a simplification.
There is. A really crucial comment comes from R.J. Manthar. In 2009, he pointed out an equivalence.
An equivalence to what? What did he figure out?
He realized that counting these specific non-integral partitions is actually the same as counting the solutions to a particular inequality.
Ah, okay. So the abstraction maps onto a concrete counting problem. What's the inequality?
It involves square roots. It's a sum of the square roots of 4 variables.
Yeah.
Sex by dollars, by 2, by 3, by 3, 12, must be less than or equal to n.
Less than or equal to n. Okay. 4 variables, 6 by 2, by 3, by 4, 2. Are there rules for these x's?
Yes, and they're very important. They have to be integers, starting from 1. And crucially, they must be in increasing order.
Increasing order. So $1 by $1 by 3 by 3 by 2.
Exactly that.
Why 4 terms? And why the increasing order? What does that relate back to in the partition idea?
Well, the 4 terms likely connect to the specific dimensionality or type of partition being studied in the original sources, and the increasing order. That's standard practice in partition theory.
Ah, right, to avoid counting the same combination of parts multiple times just in a different order. Like 2 plus 3 is the same partition as 3 plus 2?
Precisely. So imposing the order 6 get a lollar by 2 guy lard by 2 by ensuring each valid combination of square roots is counted only once. It makes a potentially messy problem countable.
Got it. So this sequence, A000347, authored by Sloan himself, gives us a computational handle on this complex partition idea via summing square roots.
That's the essence of it. But the story gets even more interesting when you look at the references.
Okay, where else does this pop up?
Well, there's a paper from 1951 by Agarwala and Alok and connects this sequence directly to statistical mechanics.
Statistical mechanics. Wow. Okay, it's unexpected. We're talking physics now, like modeling gases or complex systems.
Exactly. The paper's title is literally Statistical Mechanics and Partitions into Non-Integral Powers of Integers. It draws a direct line.
So how does counting solutions to sex by doll, plus by 3, plus by 3, plus by 4 doll relate to, say, energy levels in a physical system?
It suggests that the mathematical constraints here, the 4 terms, the square roots, the ordering, might actually model constraints found in physical systems.
You mean like how energy or some other quantity might be distributed among parts of a system?
Potentially, yes. The number of ways a system can arrange itself, perhaps its energy states, could follow this kind of mathematical partitioning rule. It shows how number theory isn't just abstract, it can provide the language for physics.
That's a really powerful connection. So to kind of wrap up our dive here, 000347 starts as a niche idea about non-standard partitions. Shows incredible growth, gets simplified into counting solutions to an inequality with ordered square roots,
Right.
and then connects surprisingly to the physics of large systems via statistical mechanics.
That sums it up nicely. It really bridges disciplines.
So here's something maybe for you, the listener, to think about.
Yeah, this connection raises a fascinating question. How often do these elegant mathematical constraints, like ordering the $60, turn out to be more than just convenient math tricks? Could they actually reflect fundamental rules about how things are structured or distributed in the physical world? What really strikes you about that link between pure counting and statistical physics?